Okay, so thanks a lot for the introduction and for the invitation. So I'll try to be as down to earth as possible, even if maybe the abstract was a bit intimidating. And I'll try to at least introduce the main problem I was thinking about in the last few years. Okay, and actually I will stick to instead of speaking about general Schumann varieties, which might be a bit difficult for people who have never worked with Schumann varieties. Let me actually fix a very specific example. So I fix a positive integer, and the Schumann variety that I will work with is the moduli space of principally polarized abelian varieties of dimension G. So something we can relate to, okay? And already in the case G equal 1, so the case of modular curves is interesting enough. So if you want just think about modular curves, okay? And actually, you know that modular curves, you have the open modular curve, then you can add the cusps to make it to make the modular curve proper, projective. Okay. Also, in this case, at some point in my talk, I will need some toroidal compactification. That depends on some combinatorial data, some cone decomposition that I stress by putting this sigma there. Okay, it's not unique as in the case of modular curves. So for higher genus, there's a choice involved. And let me start with the period map. Over the complex numbers before we move to characteristic P. Okay, and let's see what we know there. Well, there we know things very well. So we know that actually that our moduli space is actually uniformized by the Siegel upper up space. Right, so these are simply the G times G complex matrices with the property that they are symmetric and that the imaginary part is positive definite. So for G equal 1, you have the usual Poincare upper up space plane, okay? And actually this is a uniformization map in the topological sense, okay? And to draw here, actually, you can associate the abelian variety A to O, which is simply C to the G modulo Z to the G plus the image of the lattice spanned by the first G standard vectors of C to the G, and then other G vectors, which are the column or the rows, as you wish, of your matrix tau. And actually, the period map that comes from Hodge theory, so I put pi h, h is for Hodge, goes actually to the Grassmannian variety. So this is the Grassmannian of G-dimensional isotropic subspaces of C to the 2G, which we endow with the standard symplectic form. Okay, so there's a symplectic form that makes sense to talk about isotropic subspaces. Okay, and actually, let me reinterpret this diagram. So since we don't have blackbirds, I have to rewrite my diagram. Because if instead of starting with a tau, I start with a principally polarized abelian variety, okay, what actually I can do is, and actually these are all the points in the fiber of this map pi here, okay? So pi minus 1 of A simply consists of pairs which consist of A and a certain gamma, okay? Maybe I put gamma Z, where gamma Z is actually an isomorphism of the Betti homology of A with Z to the 2G, okay? And this isomorphism should respect on, certain pairings. So on H1AZ, you have a pairing coming from the principal polarization. On Z to the 2G, you have the standard symplectic form, okay? And you want this to be respected. And then actually, so I start with an A here, and then the map here associates to a pair A gamma Z, actually the following isotropic space. So if you take, so C to the 2G can be identified by taking the complexified version of gamma with the Betti homology with coefficients in C, and actually by Hodge theory, and that's why here I called pi Hodge my map. This goes to the Lie algebra actually of A, and this map is surjective. So you see that the kernel of the composite, so this I call simply alpha of C, the kernel of this map inside C to the G defines, so it's a piece of what is called the Hodge filtration, and it defines a G-dimensional isotropic subspace, okay? So this thing here belongs to G, to GC. Okay, so that's a very useful period map, okay, which has been used actually to, for example, study the Oort conjecture and so on. And what I want to convince you is that actually nowadays we have a very nice analog of this. Over CP. So the analog of the complex numbers. So the complex numbers are simply obtained from Q by completing with respect to a certain topology and then taking algebraic closure. Here we do a similar object, a similar process. So we take the periodic numbers, we take an algebraic closure, and then we complete, okay? So my program made it into a triangle, sorry about that. And actually the same diagram that we had before, we have already also in this context. So we have a space which uniformize my moduli space, okay? And actually I call pi this map again. And if I have an abelian variety here, the inverse image consists of a pair A gamma P, where this gamma P, well, here we don't have the Betti homology, but we had what was introduced in the previous talk. We have the p-adic Tate module of A, okay? That's a ZP module of rank 2G. And I simply fix such an isomorphism, again, compatibly with the, on the one hand, the standard symplectic form on ZP to the 2G, and the pairing coming from the Weil pairing and the principal polarization on A. Okay, so you have such pairs. And actually, you also have a map, pi Hodge Tate. This is due to Scholze, actually, which goes to the Grassmannian variety as the CP points of the Grassmannian variety. And actually, it works as follows. So, so maybe I'll put it on this side. So using my gamma P, so you have an isomorphism of CP to the 2G with the Ekedahl homology with CP coefficients of my abelian variety. And here by p-adic Hodge theory, so this is the so-called Hodge-Tate decomposition, you have a map that is a slight difference from what happens over the complex numbers. And here it goes to actually H0A omega A, but it's a surjective map. And this I call again alpha P. And this HT here goes is coming from this Hodge state that appears over there. And then if I take, so this is a gamma of CP inverse. If I take the kernel of alpha P composed with gamma CP inverse, that is contained in CP to the 2G, and one can prove that in fact this is a G-dimensional subvector space, CP subvector space, which is isotropic with respect to the standard symplectic form, and it defines an element over there. Okay, very nice. Now, the nice thing is that in mixed characteristic 0P, as we saw in the previous talk, we can also go reduce things modulo P. And for that, I need my compactification that I introduced before. Because the CP points of a compactifications are simply the OCP points. So let me shrink the page so that everything fits. And OCP points I can reduce modulo FP bar. Okay. And similarly here, actually, so the Grassmannian variety is actually a complete variety. So by the evaluative criterion, the CP points and the OCP points are the same. And again, also at this level, I can reduce modulo P. And I get two maps, which are Q1 and Q2, which are actually, I see them as two sort of discrete period maps. Okay, so let me move forward, increase the size, and rewrite the diagram that we had. Okay, so we have this analog of the Poincare space, the CP points. So here I'm bluffing a bit because this I'm describing for you only the points of the space, but this actually has a very nice topological structure. It's also a local ring space, and it's a perfectoid space. Okay, but here I am happy with describing simply the points. I won't need more than that. So I don't need the structure, at least to state the problem of local ring space. And here we said we have two maps, Q1 and Q2. And the problem that I was intrigued by is the following, that on these two spaces in characteristic P, using in different ways Frobenius, you actually have two very natural stratifications. So on the one hand, you have the Ekedahl Oort strata. This classifies actually, so if you have an abelian variety here in characteristic P, classifies the P torsion that now is not something Ekedahl. It could be that over FP bar this has is zero dimensional, but you can make sense of the kernel of multiplication by P on this abelian variety before taking FP bar points, as was done before. And that actually gives a group scheme. So classifies AP as group scheme with its own principally, so it's a principally polarized group scheme. And Oort proves that actually over FP bar, these group schemes arising in this way fit into finitely many possibilities. And so you stratify the moduli space in characteristic P by putting together all the abelian varieties that have isomorphic P torsion. Okay? And this strata is actually, so these strata are indexed by a certain subgroup inside W, which is the Weil group of GSP2G. Okay. And actually, if I have an element in here, I will denote EOW the corresponding stratum here. Okay, so using this correspondence, and actually there are very nice results by Ekedahl, Oort, and Mon and Vedorn and many others, and actually former student of mine for general Shimura varieties, that tells that this stratification is smooth, and that, for example, the dimension of the Ekedahl or strata, it's simply the length of W as an element in the Weil group. So it's a very nice description of the combinatorics of this stratification. And there is also an order relation on W plus, which tells you when a stratum describes perfectly when a stratum is in the closure of another stratum. Okay, and it's an order which is not exactly the Brua order, but it's closely related to the Brua order. It actually took a while to find it. And on the right-hand side, you have the Lusztig stratification that actually classifies for Z a subspace of Fp bar to the 2G, which is isotropic of dimension G, classifies the relative position of Z and phi Z, where phi is actually the Frobenius on Fp bar to the 2G. So you apply Frobenius component-wise, you get an automorphism, you have a subspace. This map transforms it into another subspace, which is again isotropic of dimension G. And you look how these two subspaces are related. Maybe they intersect, maybe not. What is the dimension of the intersection? Whether this intersection is Frobenius stable and stuff like that. Okay. And also in this case, actually, this is actually indexed by a subspace, subset. It's not a subgroup, a subset of the same Weil group. And you have that actually, so if you have, as before, a W prime in here, you have actually a corresponding Deligne Lusztig stratum in here via this correspondence. And actually, again, the length of W prime is the dimension of this Deligne Lusztig stratum. And actually, there is also an ordered relation on this index set that perfectly describes, it's again combinatorically defined in terms of the Brua order that defines the closed relation of this stratification. Okay. Example: G equal 1. You have a modular curve. In this case, you only have only two Ekedahl Oort strata. You have a modular curve in characteristic P. You know that elliptic curves can be ordinary. And this actually has dimension 1. And then you have certain points, which are the supersingular points. And also on the Deligne Lusztig side, you have two Deligne Lusztig varieties. You have the Fp bar points of P1, to which you take out the rational points over Fp, and then you have P1 Fp. So these are the isotropic subspaces that are rational over Fp. They are fixed by Frobenius. And the funny thing that was observed by Scholze and Karajanni, actually Scholze for AG, is that if you apply Q2 composed Q1 minus 1, remember that we have this correspondence, right? So I take the inverse image by Q1 and I take the image of Q2. These two loci are flipped. So the one-dimensional locus is actually mapped to the zero-dimensional locus. And actually the supersingular locus, which is zero-dimensional, somehow it becomes, when you take, oops, I see that I flopped the two, so it's Q1 minus 1 composed with Q2, sorry. it's actually one-dimensional. Okay, so there is something. So there is not a perfect correspondence, but still. So there is a shift of dimension, and well, let's see if something can be said in for higher dimensions. So let's see the case G equal 4, and in this case there are 4 Ekedahl Oort strata and also 4 Deligne Lusztig strata. So that's already a nice coincidence. And actually, so you have the dimension. This is a threefold. A2 is a threefold. And you have the open locus, which is consists of ordinary abelian varieties. So then you have a dimension 2. This consists of abelian varieties whose p torsion, if you take the FP var points, you know that this is an FP vector space of a dimension at most 2. It is 2 if your abelian variety is ordinary. Otherwise, it has dimension 1 or dimension 0. And when it's dimension 1, we say that it's of p rank 1. And then dimension drops if actually you have something which is super singular. And then you have a dimension 0 locus where it's super special. So super singular means that it's isogenous to the self-product of a super singular elliptic curve. And super special means that it's isomorphic to the self-product of a super singular elliptic curve. And what happens on the other side? So here, so you remember that we have a z inside fp bar to the 2g. And actually the dimension 0 locus in this case is the case when z is defined over fp, okay? Which amounts to say that its Frobenius transform is equal to itself, okay? So that's the dimension 0 thing. Then you have the locus when z intersected phi z is one-dimensional and fixed by Frobenius. Then you have the case when z intersected phi z is one-dimensional but not fixed by phi. And then you have the final possibility. So this is actually this 4, so z is two-dimensional, when the intersection is simply 0. And again, if you compute a bit, you see that the ordinary locus goes to the 0-dimensional one, the dimension 2 locus goes to dimension 1 locus, dimension 1 gets two-dimensional, and the dimension 0 locus is actually the three-dimensional. So there is a flip in the dimension and in the correspondence. Okay. Okay, so I was very intrigued by this phenomenon. So which tells us that coming back to our correspondence. So it's telling us that this Q1 and Q2 is really like blow up, blow down map. Okay, so for example, in the modular curves, we have points here. Okay, so they are blown up in mixed characteristic. Okay, and you have an exceptional divisor, and then the ordinary part of your elliptic curve when you apply Q2 gets contracted, and instead this exceptional divisor maps surjectively on P1. Okay. Okay, so I can now tell you what I can prove. So this is my theorem, and the theorem is that there exists an order reversing bijection sigma 0 that can be described very explicitly. It's the multiplication by an element in the Weil group. Okay, order reversing where on the left hand side we consider the Ekedahl Oort order, and on the right-hand side, we consider the Deligne Lusztig order, okay? Such that if the inverse image of an Ekedahl Oort stratum intersected with an inverse image of the Deligne Lusztig stratum is different from empty, okay, for some W in W plus and W prime in W minus, then we must have exactly the phenomenon that we saw in the cases G equal 1 and G equal 2. So the ordering, so the W prime is less or equal for the Deligne Lusztig order than sigma 0 of W, or equivalently, we have that W is less or equal in the Ekedahl Oort ordering of sigma 0 minus 1 of W prime. And also there is, since we know dimensions, we know actually, so this also this matching of dimension, the fact that going through Q1 minus 1, Q2, there is a shift in dimension, is explained by the fact that actually this order reversing bijection has the property that the length of the image of some W via sigma 0 is actually equal to the dimension of AG, which is G times G plus 1 over 2, minus the length of W. So for example, if you have the ordinary locus, in that case, L of W, the corresponding L of W is equal to G times G plus 1 over 2, and the corresponding sigma 0 is the trivial element, so you get a dimensional length 0 element. So the corresponding Deligne Lusztig stratum where your ordinary locus length is actually 0 dimensional that we saw in this example. And in fact, as a corollary of this type of argument, one can prove that in fact the Ekedahl Oort strata are different from empty for every W in W plus, which in this case was a result due to Oort himself in the case of AG. But for general Shimura varieties, actually it's a new result. And I guess I'll stop here. So thanks for your attention.